Good evening, all. For today's second session, we are pleased to have Dr. Satyendra Kumar Mishra. Good evening, sir. Very warm welcome to AICT sponsored Atal FDP on emerging frontiers in quantum technology and communication. It is my great privilege and honor to introduce today's distinguished speaker, Dr. S.K. Mishra, sir, an eminent speaker and expert in the field of quantum communication and sensing. Uh, Dr. Satyendra Kumar Mishra, sir, is a senior researcher and associate professor at the CTTC Spain, working in the space and resilient communications and system unit, with an MTech in nanotechnology and a PhD in physics from IIT Delhi. He has held research positions across Hong Kong, the USA, Canada, and Denmark. His work focuses on quantum communication, optical and photonic sensing, fiber optics devices, and advanced nanomaterials for next generation communication and sensing systems. He has authored more than 140 scientific publications and serves as an editor for several international journals and conferences. He is editor of IEEE Sensor Journal, Scientific Reports, and Discover Journals. Respected sir, participants are looking forward to your talk. I request you to please begin the talk.
Thank you, Dr. Mishra, to introduce me. Now I am going to share my screen. And please let me know if my screen is moving. Sometimes I have faced a problem. So please stop me if my screen will not move with the presentation, okay?
Sure, sir.
Yeah. So, so good evening, everyone. My name is Satyendra Kumar Mishra. Currently, I am working as a senior researcher in Center for Telecommunication and Technology, the Catalonia, which is currently in Barcelona, Spain. And I have been joined here as a senior researcher 2.5 years before, where I am leading the satellite-based quantum communication and sensing research line here. And currently, we build the lab for the satellite communication. We have the some of the equipment which is, and also we are pushing this research in the next generation. So my lab is known as the AI Quantum Optical Network Lab. So as you know, everybody is working in AI, so I can't stop this one. So even my core background is not AI, but we just start with to do some research with AI also. Uh, s- so I just change my slide. Is it fine, right?
No, sir.
This is the problem. I always now.
Yes, sir. Yes, sir.
So I think I have to be do something else. Yeah, maybe this can be. So, I will go in this mode only. So we CTTC usually in the is the Castelldefels area. We have the two building, and we are the part of the University of Polytechnic Catalonia, but we are public research institute. And I think you also know the ICFO. Here is the ICFO. We have the 10-meter distance between CTTC and ICFO buildings, and we are the like a public research fund research institute. We in usually in Spain, every research institute have his own program, and they are focusing the some of the research objective. So we are more focused on the telecommunication. My research
Uh,
institute more focus.
sir,
Sorry,
the
yeah,
slides are not visible, sir.
really? Okay.
Yes, sir. Yes, sir.
Wait. How about now? It's okay.
Uh, Not visible, sir.
Why? I share the screen. How about now?
Yes, sir.
No, it's okay, right?
Yes, sir. Yes, sir. Visible.
Yeah, so like our research institute is here, CTTC is here. We are neighbor of the ICF. This is the UPC Polytechnic Catalonia, and this is we are near the beach. That is the area known as the custody file. So basically, we are non-profit organization. We have the this 60 of more running funded that can be European and industrial project. We are working on the current cutting edge laboratory, state of the art, and we have our own test bed. We more focus on the fundamental applied research. We have a lot of international collaboration. So our CTTC, as I mentioned, non-profit organization from a public initiative with a high degree of self-financing, open to participate other public and private body, as well as partnership with the industrial and business sector. So is it visible? Sorry.
Yes, sir. Yes, sir.
Yeah. So our mission is excellence flagship center to serve bridge between academia and industry at a center that influence the future path by communication technology, system network, and geomatics. Now, CTTC also expanding the more different research area, but which will be become in the near future. I am the part of the space, and we have the nine research unit where I am the part of the space and readiness communication system. Where our research is more focused on space interface communication and subsystem, space network resource control and management, and space technology spanning terrestrial and system application. So my slide is visible, right?
Yes, sir.
So as I mentioned that I am leading the lab which is more for the AI and quantum optical networks. Since when we are talking about the quantum communication, we should not forget about the optical communications. This is the even I can imagine the optical communication is now more popular due to the when the quantum communication came, since the we like after the coming the quantum communications, and people start to also more investigating for the standardization and device development for the optical communication. So the core infrastructure and capability of the CTTC is the quantum, and we have the quantum photonic test bed, such as some QKD test bed, discrete variable, continuous variable, entanglement based system for secure and quantum communication protocol. We also developed the channel and turbulence emulation, which is free space optical link emulator system of control simulation for FSO communication link to understand and mitigate atmospheric effect. Since, as I mentioned, we are more working on the satellite to ground communication, it is very hard to every time you can get the satellite data for your communication system. So when I joined, we have start to develop our free space emulation system. So we don't need the really every time the satellite data. We can emulate, at least we can predict the satellite to ground communication using this emulator in the lab. I also promoted the orbital angular momentum based hardware, which we orbital angular momentum based communication. We have the different type of hardware. We have turbulence phase scan generator, synchronization high speed electronics, and control indoor FSO path. So in case of the continuous key distribution, you can see we have the different type of this different type of the quantum test bed, such as discrete variable, continuous variable, and entanglement. And different type of test bed have the different application. And we are investigating in the different part of the this type of test bed. We have also 110 gigabits real-time oscilloscope, 20 gigahertz arbitrary wave generator, and quantum random generator technology, and advanced photonics platform. We have the facility to characterize the setup, alignment stage, measurement tool, and this can AI. We are also supporting more AI nowadays and programmable photonic processor. We have the strategic we are very open to do some strategic collaboration with the native quantum layer, integrated QKD test bed, quantum secure research collaborative framework, and physical ground truth multi physics digital twin. So let's start with since the objective of the presentation. where I am going to discuss about the little bit about the quantum Q distribution, little bit I discuss about the quantum internet, and then I will start to discuss more about the integrated devices, integrated photonic devices and sensing application. So when we are discussing about the quantum Q distribution, the QKD leverages immutable law of quantum mechanics to establish cryptographic key with the probability security. So there is the no cloning theorem. Unknown quantum state cannot be perfect copy, and endeavor cannot be intercept and duplicate a quantum key without altering the original state, leaving the detectable trait. So what is the measurement disturbance? Measuring a quantum system disturbs its state. Any attempt by an endeavor to measure the quantum state carrying the key will introduce the detectable anomaly. And quantum entanglement, when discussing entangled particles that share the same fate regarding of the distance, measuring one instantaneously influences its entanglement partner, providing the basic of secure key generation. For classical versus, if we are talking about what is the classical versus security, classical crystal rely on the computational difficulty, while QKD secure the based on the fundamental quantum mechanics principle that are probable secure. So when we are we actually I will more talk about the discrete variables since they the different type of QKT system, but the since I mentioned we are more focused on the satellite to ground communication, satellite communication, and then when we are talking about the satellite communication, we have more focus on the discrete variable QKT system. Since the data is going to encode it in polarization state, and they have the low loss as compared to the QKD continuous variable QKD system. Another thing is that now the satellite to satellite communication research has been growing due to the different type of the war is coming, and they realize that now the fiber optics communication is not secure anymore. And this is the one of the initiative has been done by the Europe, and NATO group are more focusing to the build a satellite communication, pushing the satellite communication day by day a lot. And also, when we are discussing about the fiber optics, the losses are a lot. This is also creating the boundary to extend the quantum communication for a long distance. Then in this case, also the satellite communication is very popular nowadays. So the key characteristic of the discrete variable use single photon of the quantum carrier, encode information in discrete properties, example polarization, rely on the measurement distribution principle of security, and why it matter. DBQKT provide a foundation for secure communication based on fundamental quantum principle resistant to the computational attack. The most widely recognized DBQKD protocol developed by the BB Burnett and Brass in 1984, but there is also we have also developed the quiet state DBQKD system in our lab. But when we talk about the DBQKD, BB84 protocol for DBQKD allows transmission, allows generate the random bits and encode them into the photon polarization state using random basis. Bomb measures receive photon, measure them randomly chosen basis recording the outcomes. Basic recurrent allies and bomb publicly compare bases used and keep only the matching instant and formatting shifting the key. And in the detector, allies and bomb compare a subset of bits to check of error. If error rate is acceptable, they proceed with the key generation. So when we like as the in the satellite communication, there also people are talking about the teleportation and other things. Then also entanglement based QKD system is coming in the nowadays, and we are talking about the quantum entanglement. Measurement of one entangled particle stance influences its partner regards of distance, and security advantage is based on the Bell theorem. Indo-European breaks entanglement correlation detectable during key generation. So when E91 BBM 92 protocols, entanglement pair generation, quantum secure generating entangled photon pair, independent measurement, and basic comparison. We using the then Bell. We are thinking about the Bell theorem and endotropic detection, where ever measurement breaks entanglement and correlation deviation from the expected value, and key discarded if the Bell test fails. So comparison between the discrete variable and entanglement based security. Why I again try to tell you the my main objective is the satellite based communication system. So we have the DB but I never I always try to think about what is the comparison. So about the DBQKD and entanglement QKD systems, the source requirement weak coherent pulse are true single photon sources, and entangled photon source such as SPDC. Security rely on the measurement disturbance principle, endotropic induced the detectable error, rely on the Bell theorem violation, endotropic breakthrough entanglement correlation. And satellite typically act as a trusted node, establishing separate key with ground station and combining them. And can act as a non-trusted source, disturbing entanglement pair and two grounded state only. The protocol for the DBQKD is the most probably BB84 protocol and E91 for the entanglement based QKD system. Technical challenges for the satellite. When we are the most the challenging is the PAT system, position acquisition and tracking. This is the one of the biggest problem in all the optical communication. And since we know the satellite communication is more related, content communication is more related, more uh, like a optical communication, and in the case of the PAT system is also challenging in the low power of the quantum signal. So we just bought a telescope which from the Astrolight, which is the part of the Lithuania. We have the this telescope have the quantum capability to transmit the data from satellite to ground, and we are testing now. So but the problem is the pointing acquisition and tracking maintenance precise optical link between the rapidly moving satellite or ground station LEO satellite move to the high speed. As you know, when we are talking about the PAD system, we are also talking about the fiber coupling, single mode. Nowadays, people are more working on the single mode fiber coupling, with which is going to connect with our transceiver. And then this is the one of the problem when your satellite is moving, it is very hard to tracking, and it is very hard to receive the data in the single mode fiber. The link losses quantum signal experience attenuation loss over long distance due to the beam diffraction, atmospheric turbulence, and in the lower wavelength 20 kilometer at significant loss, especially for the uplinks. And when we are talking about the background light, stray light during the daytime operation increase the quantum bit error rate. QKD is similarly at the nighttime actively part of current DBQKD system and space environment. This is another thing. QKD component must withstand vacuum, microgravity, radiation, and extreme temperature fluctuation. Radiation can damage single photon detector over the time. Overcoming, and I can tell you, definitely for the few years, people are going to. You can see all the papers should be going to work on this type of challenges, either theoretical, either experimental, and some of the challenges people try to address. But when you are going to the reality background, it is really not a theoretical background. The reality background always has been problem. But when we are discussing about the reality background, this challenge is going to address, and people are working on that. Overcoming these challenges is crucial for reliable global quantum communication network. So, take, future outlook and application. Robust space grade component development of quantum light sources and detector capable for withstanding radiation, temperature fluctuation, and vibration during the launch. QKD satellite constellation, advanced protocol, and quantum internet infrastructure. These are the future outlook and application is going on satellite. QKD will enable unconditionally secure communication across the global distance revolutionization cybersecurity in the quantum era. So this is the Y satellite for the QKD. You can see this as I already mentioned. Now I am going to discuss a little bit about which I am trying to do with my PhD student. And we are working on entangled swapping, purification, and quantum repeater, foundation of the quantum internet. As I mentioned that one of the main problem is the low loss. So we need some, if you want to go communicate with the data for the long distance, we need some type of repeater. Here we are saying the quantum repeater, and this is the foundation of quantum internet. So motivation of vision of this type of work is classical internet scalability limited by the bandwidth, energy cost, and signal regeneration. We here I have mentioned some of the references which will come in the end of this topic. By the end of the 2000, the world internet data volume will be the reach 180 gigabytes, with each person producing roughly 60 gigabyte daily, far more than the current network can handle. The quantum internet enables secure distributed quantum communication using entanglement. However, the direct transmission of entangled photon through the optical fiber is severely limited by laws. Even the state of the art ultra low pass fiber is still saying 0.16 dB per kilometer, and the survival probability of entangled photon pair drops 10 by -2 after only 100 kilometer. So it means that if we are talking about the entanglement photon for the communication, the fiber is not ideal carrier for this type of communication, so leading the exponential suppression of usual entanglement state, which is ultimately motivate for the secure pre-space quantum communication in entanglement swapping and quantum repeater mode. So what is the entanglement sorting? Direct entanglement transmission suffer exponential decay of the e to power minus alpha. The non-Coulombic theorem forbids copying of quantum state. And if you go Jokoxi paper 1994, what he described entanglement swapping enables two photons that over-interacted and never shared a common path to become entangled in the figure, achieved via a joint Bell state measurement on photons, one each from the entanglement pair A, B, and C, D, and have shown that resultant photon pair successfully violated and the Bell inequality. So what is the foundation entanglement purification and repeater? Entanglement purification allows two distant party to distill a smaller number of nearly perfect entangled pairs from the larger ensemble of noisy and partially entanglement ones. So for a smaller distance, we can get a nearly perfect entanglement as compared to larger ensemble for noisy and partially entanglement one. The purified high fidelity entanglement can take serve as a reliable quantum channel for teleportation or key distribution. And that's why I am saying now we also working on the teleportation, quantum teleportation, where we are more discussing about the quantum entanglement photon, and we currently with the collaboration with the University of Autonomous Barcelona and also one of the Rice University in the United States, we are and our role is that we are developing this test bed we are developing in CTTC Barcelona currently, and we are planning to exploit the quantum teleportation with the entanglement system. But the success probability of distributing initial entangled pair itself decreases exponentially with the distance. And if it means that if we want to communicate this type of system for long distance, this is not a ideal case. So what is the solution? Then this comes the quantum repeater. To solve this quantum repeater architecture, divide the total communication length into shorter length. Like within each entanglement can be generated, purified, and then extended stepwise for the entanglement swapping and further purification. And in the shorter way, we can say we need a more HAP system for the satellite communication. If we want to go in this way, this is the one of the ideal example if we can consider for the satellite communication. And together these two processes, entanglement purification and quantum repeater, from the operational foundation of the quantum internet. So the foundation of purification protocol, Barnett et al. First introduced the concept of entanglement purification protocol, introduce a method for transferring a supply of imperfect entanglement pair discarded by noise and decoherence into a smaller assemble of nearly perfect singlet using only local operation in classical communication. Concept, they consider two distinct observers, Alice and Bob, who share multiple copy of mixed two-qubit state described by density matrix X. And the goal is still distill from this copy subset into fidelity arbitrary close to unity with respect of the Bell singlet, which represent the psi minus, and which is equal to the here, which serves as a maximally entangled resource for the teleportation. The mixed input state as a Warner state is is described by this here, and the purification procedure proceed through a sequence of local bilateral operation, which is poly rotation, bilateral NOR gate via and measurement here coordinated by classical communication. After applying bilateral control NOT gate operation, ideally identically by Ellis and Bob and corresponding qubit of two entanglement pair, so source and target, both parties measure the target pair along the z-axis and retain the source pair. Only both measure outcomes coincide. The further the selection along the z-axis by applying the poly-z gate increases the singlet fraction of the remaining pair, realizing the recurrent relation. And the new fidelity f dash is always greater than f for all f is greater than half, indicating that any Warner state with f greater than half can be iterably distilled to near perfect purity. And this threshold distinguish entangled sources that can be purified from those that cannot. And the process can be recursively applied, generating the asymptotically pure entangled state at the cost of reduced yield. The foundation purification protocol is here. I am not going to discuss too much about that. But people also using the polarization beam splitter in the case of the C0 gate equivalence, while Burnett protocol laid the theoretical groundwork. It realized that havingly on the quantum control NOT gate operation whose realization at the time was beyond the experimental feasibility. So how we can experimentally feasible then addressing these challenges, Pan et al. Presented experimental viable purification scheme employing only the linear optical element, notably known as the polarization beam splitter, to perfect the equivalent logical function of the C0 control NOT gate. In their approach, entanglement qubits are encoded in the polarization of the photon, and two identically mixed pairs shared between Alice and Bob, which is described by here. The purification process replaced the bilateral CNOT gate by a PBS acting as a comparator of polarization purity. When two photons enter the PBS, two different input ports and one photon exhibit from each output port, this event indicates that the two photons had the same polarization, both HRB. The polarization beam splitter has projected the two photon system onto the subspace of equal polarization, corresponding exactly to the condition both qubit possesses equal logical value in the bilateral CNOT operation used by the Burnett et al. For the entanglement purification. So pan selection of four mode cases thus implement the same condition as a Burnett Baxa based method optically with the same fidelity transformation. And this realizes succeed with the half of the probability of the biaxial gate achieving near precision using readily available component, removing the need of coherent quantum gates. So this is the something you can study in the sum of the paper, which also we are realizing here. And then more logically, these are the mathematical equation which is going to study about the, and further people also did some experimental demonstration with the entanglement swapping with the two state. And here they use the AUV pulse passing through a nonlinear crystal, create an entanglement photon pair, uh, photon pair 1 and 2, and then photon 2 is sent to the beam splitter. And then beam after reflection, the same UV pulse produces a second entanglement pair 3 and 4, and photon 3 is also directed to the beam splitter. When photon 2 and 3 yield is a coincident detection output, they are projected into the state, and this Bell state measurement project photon 1 and 4, which never interacted into the entanglement state. Their correlation are analyzed by measuring the coincidence between detector, which is D1 and D2, D1 and D4 at a various polarization angle using the rotatable half-wave plate and narrow band pass filter in front of each detector, which we are going to keep here. And these fourfold coincident detection confirm that entanglement swapping between the photon 1 and 4 has been successfully achieved. Experimental demonstration of multi-stage entanglement swapping also has been done. You can find in the some paper, and this multi-stage entanglement swapping is also has been done here. What I am saying, people also demonstrated in the similar in the extended way multi-stage entanglement swapping, and we are trying to also do the simulation. We are trying to do the simulation about this to check how what the experimental performance, how it is going to optimize with the theoretical one. These are the reference where you can get this type of this all the paper information, which is which I have been before discussed. The another QKD system which I am more pushing nowadays is the high dimensional encoding, where I am talking about the orbital angular momentum encoding system here. So as I mentioned that my division main objective is the space quantum communication promises unparalleled security and efficiency for data transmission by leveraging quantum mechanics. The major part of the, if we have tried to understand, people talk about different way, but we can think about the in the scientifically the major problem is the photon loss, signal attenuation, and the need of robust error correction. And then we can say, okay, the machine learning and AI intelligence can going to help, and now people are implementing about AI on the device. Let's see in the near future, maybe 1 or 2 years, you can see something here. So machine learning and artificial intelligence offer innovative a solution to this problem, potentially transforming quantum communication into reliable and scalable technology. Even my student, and we are trying to, when we are talking about the satellite communication or ground communication, there is the one very important parameter and people in the hardware perspective is the adaptive optics. So me and my student already we are proposing something which is going to materialize soon. We don't need adaptive optics if we are going to use using the artificial intelligence. We have some result, but I can't show that is this is under the patent process. But but we are thinking like, if you go any type of free space optics and satellite based communications conference, maybe 50% people are talking about the adaptive optics. But my question is that really we need adaptive optics or not? That's why we are thinking about the, can it is a, we can create a something AI a machine learning algorithm. So we up to now develop the quasi adaptive optics, which is we approved from the European Space Agency, and we have the we already presented our data, and that is the already get a very good recognition there. But error, but identify challenges for the quantum communication is the global QKD network, synchronization, error correction, photon loss, and quantum efficiency. And this is the, whenever, as you know, quantum communication devices is now coming. So step by step, people are going to identify the different way, which part of the people need to focus. This is depend upon the which type of research you want to do. If you can see in this perspective, this is not a one type of research. This is the plenty of research. Like if you can see about the quantum key distribution protocol, hardware, photon loss, then you can think about the meta surface, how we are going to increase the quantum photo detector, error correction, and noise reduction. When we are discussing about, then we can say, okay, can we develop the algorithm, machine learning, AI or not? And synchronization and coordination, then the difference. So this is not the quantum communication or quantum communication system. This is not a 1% topic. This is going to visualized by the people, have their own expertise, and they are going to like improve the quantum communication system in their own expertise and own area of research. So that's why I say this is the like open research. Somebody go to say, okay, I can make a very good quantum detector. I can enhance the sensitivity. That's is good, but it doesn't mean the another way we can't enhance the sensitivity. When I have when I have started to study about this protocol, people are talking about SNSPD, single nanowire single photon detector. But currently, we are able to achieve the DBQKD protocols with a single photon detector, since we have the better efficiency. So this is the why I am saying the different area of research to investigate about the free space optical quantum communication. So the photon loss and signal attenuation, quantum teleportation experiment, like whenever the loss of anything, this is the problem. Quantum teleportation experiment often involve the transmitting photon over the free space channel, and this channel suffers from attenuation, which reduces the detection rate of simultaneous photon detection. And this is the one of the reason why the CBQKT is not more popular for the satellite communication. Attenuation can be caused by the absorption, deflection, and turbulence in the air. And the goal is to minimize these losses to enable efficient the quantum communication. Quantum key distribution, then we have the different type of challenges and synchronization and coordination, then global QKD system. So when we are talking about the quantum key distribution is high dimensional encoding, I prefer to I prefer to elaborate more about the orbital angular momentum QKD system. Be honest, when I joined here, people are thinking this is not going to work, but now even the ESA, European Space Agency, approved this, and they have been exploring since this is the one of the possible solution, and you can find that the high dimensional QKD system people are talking about that. So there it can be enabled, but there's another feature of the OM QKD system. Only the problem is the this type of OM QKD system is the divergence nature. But if but this is the we also provide some solution which can be work as a realistic scenario of this type of OM-QKD. And this OM-QKD, the next generation of QKD protocol that use the unique OM state per photon to access high dimensional encoding. Since if you are using the OM-QKD system, so you can encode the data in the OM different states, so you at the single wavelength and single polarization. So this can be give you the also the reduce the complexity of devices. You don't need the if you want to like increase the data, you need either you have to transmit the data in the different wavelength. This can increase your device complexity and increasing the cost of the device. But if you are going to use OMQKD system, that can be helpful for the reduce the cost. Also, high information capacity for photon. Unlike polarization scheme, OM can support more state per photon, significantly increasing the data throughout. And OM encoding with dimension of D4 and D8 demonstrate notable co-qubit QBR, like quantum bit error rate, like 18% to 24%, which provide greater tolerance against the noise and potential entropy attacks. We are also try to explore the OM orbital angular momentum state for the developing the PAT system in our system. But one more thing might be many people are not has been noticed that when we are using the OMQKD system, this is more resilient since there is a small mismatch. This can be easily detected by the OMQKD system, and which we are just explore, and we have submitted a paper on the basis of this. So OM also I think there's some mismatch. But what is my message here? The OM in the quantum is going to produce the more degree of freedom, and this is the one of the test bed we develop basis of the lab, and our target is going to exploit this OMQKT system for the satellite to ground. Only one of the big challenge what I am facing encoding of OM data at the higher order of the mode, since the beam size has been changed. But you can see we have getting the very good signal with the OMQKT signal with the low crosstalk, which can give the more motivation about the study about that. Now, this is about the quantum communication system, what I have been discussed, but I want to explore, and which I am also trying to explore over here, integrated optics and sensor, which has been my some of the research which I have been exploring my last different places, which I would like to describe here. So this is the surface plasmon-based sensors, which is fiber-based and polymer-based guide-based sensor. Then I would like to also describe about some type of fiber color filter using asymmetric meta surface. And then also I will talk about the OM beam in the fiber. So why my motivation is more on the OM for the satellite and ground communication is come due to the when I study about the OM beam in the fiber optic sensor. So when we are discussing about the fiber sensor, the fiber is made of the core and cladding, where core refractive index always greater than the cladding, which can give the better transmission of the light through the waveguide. This can be used for the many applications, where the fiber sensing and fiber imaging, surgery, medical, and military and aerospace application. Definitely, this type of sensor. It depends on you where you want to use this type of application for you. So in some of the application, I use the fiber, this type of sensor, where I use the surface plasmon techniques. This is to fabricate this type of sensor. The reason behind that, the surface plasmon technique can enhance the sensitivity and enhance the detection accuracy of the sensor. But what is the when we are talking about the fiber sensor? Fiber sensor is the input signal is modified by the external perturbation. This external perturbation can be anything like a magnetic field, electric field, or like a cancer cell, whatever the things. This depend upon the application. And this external perturbation, we can observe the signal in the property of the light. The property of the light can be modify the intensity of the light, phase, polarization, and wavelength. Some of the example I am going to say, which is mostly based on the wavelength change, so which I am going to discuss about that. And as I mentioned that I have been used the surface plasmon for my sensor characterization. The surface plasmon are the quanta of charge density oscillation at the metal dielectric interface, and surface plasmon exists for the TM polarized light. The reason is that when we are solving the boundary condition, and when we are considering the electromagnetic equation, what we have found that when we are considering the boundary condition, the surface plasmon is not going to excite by TE polarized light. So, and this is only excited by TM polarized light. And also this, after satisfying the boundary condition, what I observed that for the excitation of the surface plasmon, we need the two different media, and that different media have the different different sign of the dielectric constant. It means that it means that the two media, one media should have the positive dielectric constant, another media should have the negative dielectric constant. So it means that negative dielectric constant, it means we need a metal. Since metal only have the negative dielectric constant, which can give the information about that, surface plasmon can excite when we have the metal dielectric interface, and that metal dielectric interface can be responsible for the excitation of surface plasmon. But surface plasmon readiness condition, which can be observed for the sensing application. So what is the resonance condition? Means whenever the resonance means when we coming about the optics or some science point of view, one of the example, resonance means there some matching. Here we are talking about the phase matching condition. So what is the phase matching? What is the meaning here? What is the here phase matching? So it means that our wave vector for the surface planar and wave vector for of the wave of the light should be matched. So what happened when we are talking about the direct light, when we are going to learn the direct light, and when we are looking at the wave vector of the surface plasmon, we can see directly the no matching condition. It means that surface plasmon cannot be excited by the direct light, so we have to modify the wave vector, and then we need a special type of configuration, and most popular configuration is the Christman configuration. And what is the Christman configuration? In the Christman configuration consideration, we need a high dielectric prism, and we have to deposit the metal film. Since as I mentioned, for the surface planar, we need a metal dielectric interface, and then we have to deposit a metal for the excitation of surface planar. And you can see here, when the light is passing through the prism, you can see the dielectric prism wave vector, the surface plasma, the wave vector, and this wave vector has been intersect each other, means phase matching condition has been satisfied. It means that this type of configuration useful for the excitation of surface plasma. And here is your equation for the phase matching condition. So what happened? We as I mentioned, the surface plasma can be excited by the TM polarized light, means P polarized light, and then whenever the refractive index of your media has been changed, you can see in this is the plasmonic dip for the air, and when you have changed the solution here, or whatever the refractivity of the media, according to that, you can shift, you can change in the shift in the wavelength. And this is the what I try to explain, try to tell you before in my one. So my most of the application is based on the wavelength shift of the wavelength shift of the our condition, our sensor. And you can see when we change the refractive index or whatever the interaction is going on, interaction going on is that more like a refractive index going to change. And when your refractive index going to change, your resonance wavelength can be changed. And you can see here, epsilon m is the refractive index of the metal, and epsilon d is the refractive index of your dielectric media. This can, if you are changing, your wave vector can be changed. You can see here the change in the shift that clearly visualized. In the case of the characterization of the sensor, I have been working the different type of sensor type, something chemical and biosensing setup, which is here, and there the gas sensing setup. Only the uh, in my case, I have used the fiber. This is the most of the time multi-mode fiber, where I enclosed the portion and deposited the metal film with the dielectric film for the sensing region. And further, I have been create a sensor chip here, which is based on my application of study. The in our setup, I use the tungsten halogen lamp, use the microscope objective to collimate the light, and further I analyze the data with the spectrometer, which is interface with the computer. The difference is the biochemical and gas sensing setup. I have removed this our biochemical set like a test tube with the gas sensing setup, gas sensing chamber, and which is connected with the different type of gas. Otherwise, the more like the setup is similar. So just try to give one example here. There is some problem, but you can see this is my fiber core, and I have deposited ITO or gold or silver metal for the excitation of surface plasma, and further I have deposited PA polyaniline film or bromochrysal purple. There are different type of sensor I have been demonstrated. First, I have used polyaniline film, and I have passed the different ammonia gas. Since I know my objective to go to detect ammonia gas, and then what I observed that when I am changing the different concentration of gas with the optimized the sensor parameter, you can see the shift in the transmission curve. And this shift in the wavelength can give the information about the change in the refractive index or other sensing things. But if I can replace this polyaniline film with the bromochrysal purple, is the one type of dye, and what I observed that my sensor is very sensitive with the lower concentration, and also sensitive for the lower concentration. So I start with the polyaniline, but later on also I have been used bromochrysal purple for which can be give the lower concentration detection of the ammonia gas. Further, when we are discussing about the sensor, the transmissions characteristic is not very useful, since then people are asked, really this sensor is very good for the sensing or not? Then you have to talk about the selectivity. Then definitely without the selectivity, your sensor is meaningless. And if this sensor is going to detect everything, there is no useful information you are going to get the sensor. Then for this type of point of view, I have been studied this bromochrysal purple selectivity, and you can find here my sensor is very sensitive to the ammonia gas, but not sensitive toward the different gas. But then you have the question, no, this is not right. You can see we have some sensitivity here. But what happened? What is the reason behind to getting this type of sensing sensitivity is the whenever you prepare the sensor and you come in the environment, always there is the oxygen layer, O2 or O minus layer going to interact over the surface, and some of the very reactive gases is going when is coming in the environment. This going to interact with this O2 O2 minus layer, and that can give the small shift in the resonance. But this is not going to interact with the bromochrysal purple. So this can give the information about that our sensor is very sensitive to the bromochrysal purple and is highly selective as compared to other gases. Then further, I have been analyzed with the fiber for the cancer cell detection. The motivation about the then in case I have used the long period grating fiber, and in the case of this is the photosensitive fiber where we created a long period grating with the help of the in our lab the CO2 laser. The requirement of but further, we some of the group which collaborator who created a surface antibody antigen, which this antibody antigen is very selective for the one of the type of cancer cell. And here is the A549 human lung cancer cell. My objective is that can in the cancer cell there are the two type of cells, that's hypoxia and hypoxia condition. Can this type of cell can be used for detection of this or not? Then what I found that if I have the hypoxia condition and we can change the concentration of the cell, the sensor is going to show that shift in the transmission spectra, otherwise it is not going to say. And which can give the information about that this sensor is very good for the early detection of the cancer as compared to other. Further detection of glucose, I am not going to discuss, but again, I am going to discuss about the waveguide coated with graphene. So I think I have missed one slide. No, leave it. So let's discuss about some other application about the fiber metasurface, where what I have been investigate about the polarization dependent photonic crystal fiber for color filter using asymmetric metasurfaces. So as you know, whenever we have the fiber, when we dry the fiber property has been limited with the there after the drawing. So they have been limitation from the ground material and fixed optical property after the drawing. So then how we are going to this property can be transmission, polarization, focus, numerical aperture, and mode profile. So there is any way to we can change this property and we don't need to redraw the fiber or not. Then people start to think about the metasurface. A metasurface is an artificial nanostructure interface that has the sub-wavelength thickness and that manipulate the light by specially arranged meta-atom. And fundamentally building blocks for the metasurface. Those meta-atoms usually consisting of plasmonic or dielectric. These are, you can use the plasmonic materials such as gold, silver, either dielectric nanoantenna and can directly change their light properties such as phase, amplitude, and polarization. So people further integrate the advanced nanophotonic technology into optical fiber such as plasmonics, either gold or silver, either plasmonic metasurface. You can make a metasurface of the plasmonic material, and you can tune the property of your fiber. So how we did it? We have been used the single mode fiber and deposited AU layer of 100 nanometer using sputtering. And further, we draw the metasurface using focus ion beam milling method. And you can see here the metasurface, which I have been fabricated here in the Baylor University, using the focus ion beam, which is associated with the scanning electron microscopy. Here, this is the fiber where you can see this is the core area of the fiber I have been fabricated, and you can see I have been nomenclated negative structure means where the cross chain where I have removed our gold. And when I am talking, I will discuss about the positive, then it means that the structure where the cross chain have the material, our gold film, otherwise not. And other thing is that symmetric and asymmetric is the geometry of this metasurface. Means if the like length and width is equal, then I will discuss about the symmetric, otherwise asymmetric metasurface. So then then what I found that when I have been used the symmetric metasurface or asymmetric metasurface with the different polarization, I am getting the different large harmonic dip. But the thing is that the question is that this is really polarization dependent or not. Since when we are talking about the single mode fiber, we can't say this is the polarization maintaining fiber. It means that if I am fabricating the metasurface on the fiber tip and I am changing the input polarization and I am getting the different type of plasmonic dip, it is really due to this metasurface or due to the fiber disturbance or vibration. So for that, further, I have been in the polarization maintaining photonic crystal fiber. Why I use this is available in the my lab. There no reason why I use the photonic crystal fiber. My main concern is the polarization maintaining fiber. So this is the polarization maintaining. Now I further fabricate this type of asymmetric and symmetric metasurface, and this is my characterization setup. This is the fiber. This is the supercontinuum laser, and here is the polarizer where when I am changing the input polarization, and according to that, we are getting the change in the output polarization. But the thing is that the good point at that, when I am taking the symmetric metasurface means that the length and breadth is equal. Then the 0 and 90 angle, we are getting the same single plasmonic dip. But if I am taking the asymmetric metasurface. So if I am, this is input polarization. When I am changing the input polarization, we are getting the change in the output polarization. This is the simulation result, and this is the experimental result. One more thing, you have this plasmonic dip also dependent on this dimension. So, but the thing is that my concern, my idea is that if I can change the input polarization, this is the output, the plasmonic dip change or not. That say yes, and I can say this is the I demonstrated the polarization dependent color filtering effect from the metasurface on the fiber, engineering color filter to a desired wavelength range, and potential application for color filter split and polarization converter, etc. So now I am also going to talk about one interesting topic about the thick ring of fiber supporting OM orbital mode using perfect vertex beam. So whenever we are talking about the OM mode, in the OM mode, we more either in the fiber, either in the free space. Most popular is the Lagrangian beam. And Lagrangian beam is a type of optical beam characterized by their helical phase front and donut shape intensely. This is the equation which is going to talk about your Lagrangian beam. So, but in my case, I have used the perfect, but there is another type of also beam. But I will tell you, the people are also investigating the different type PRA test beam, and they try to use for the different application, and also try to study about the if we can reduce the divergence of the beam or not. The people has been developed this like basal beam or some other type of beam which is like less diverging, a quasi-diverging beam, and then but the most popular beam for the OM is the Lagrangian beam. So the Hermite-Gaussian beam. But in my case, this application is for the fiber. So in this case, we have used the ring core fiber. Ring core fiber means that your this area like core is the ring shape, and the inside and outside have the cladding. When we are talking about the OM mode in the fiber, there is another type of mode, also linearly polarized mode, and that mode have the problem, the modal crosstalk. Why the people study about this OM mode for the communication point of view? This is the low crosstalk between the mode, and but the problem is that uh, making this type of mode, you have to take the index separation is higher, and as the concept of the physics and fiber optics, if your index is higher, your loss will be increased. But the good thing is that they have the low crosstalk. We have the first time developed the sequence core fiber with the polarization purity is high. But here we have tried to learn the two different type of mode, and this is the refractive index profile for developing this of the ring core fiber. So I think there's a problem, but it's okay. The perfect vertex beam here, I actually, but whenever you have developed your fiber, like if you talk about the single mode fiber, it is already standardized, but this is not the case. But when we are discussing about the new type of fiber, the first thing is that you have to characterize, you have to know what is the loss, what is the property, what is the things. But before that, this type of fiber, there is no technique which can be characterized the loss of the fiber. So we have to study about we are going to characterize the fiber. So this is the simple setup. We use the spatial light modulator. Here, spatial light modulator going to generate the OM order mode. And here we have the laser focusing lens. Since we linear polarized light to send the one polarization state, and further we have used the Fourier lens. In our case, we characterize our OM mode, our fiber loss, using the perfect vertex beam. For generating the perfect vertex beam, we need to use the Fourier lens, and here is the fiber. We use the parameter. I will go to explain further. So this is the Bessel Gaussian beam, and when you use the Fourier function, you can get a perfect vertex beam. So what is the difference between a perfect vertex beam? The OM mode, it looks like a donut shape, but when you are changing the OM mode order, this divergence of mode order going to increase, and this length, this diameter and the width of the mode order is not, ratio will never constant. But when you use the Fourier lens, the divergence and width, the radius and this width of the fiber ratio always same, whatever the mode order you have taken. So in our case, we use the perfect, we create the perfect vertex mode, and then we characterize our fiber. Then in our case, for the characterization of this type of fiber, we use the mode dependent class. In our case, we use the we fabricate the four different length of the fiber: 10 meter, 200 meter, 600 meter, and 1.3 kilometer. This is the setup. Here, the special light modulator, we are generating the mode order 1, 2, 3 is computerized, and further we launch on the ring core fiber, and again we modulate and demodulate. The another question is that how you confirm that your whatever the mode you are launching, your launching condition right along. So then that's why we have to be use a demodulator here. So what happened if you, let's suppose that you are sending the third order mode, and after that you're also creating a phase screen of -3 after after launching fiber, and after that you should get the Gaussian mean 3 plus and minus should be 0. If you are not getting the Gaussian beam, if you, like after ordering the certain mode, it means that you are not launched the perfectly the right order mode. So you have to work in the launching condition to improve the your launching condition, and then whenever you start to get a high power, and you after demodulation you are getting the Gaussian beam, it's confirmed that you are launching the right order mode. But we also study with the real time oscilloscope, and we try to let's launch the 7 order mode, and we also check the power in 6 and 8 order mode. What we have found that the crosstalk between these is -56, which confirm that like we are launching the 7 order mode. And then when we confirm, we go to the here last slide like this way. When we confirm we are launch the right order mode, we measure the power. When we measure the input and output power in the basis of qualitatively, not qualitatively, we have measured the modal loss of the fiber. And you can see we got a very good result for the different type of fiber. This is the matrix, and we also calculated the modal power loss with the different order of the mode. So for the mode order 3, 2.14 dB per kilometer, and further we have been study with the like a higher order mode. And you can see for 1 kilometer transmission of fiber loss, not, but this is the not our objective. Our after the this type of uh, after this understanding, okay, we are able to write a right order mode. We are able to get we know what is the loss of the fiber. So we know when we are going to the data transmission, we know what is our limit and which order of the mode really we can extend. But in the OM mode of the fiber, when you are going to the higher order mode, the good thing is that when you are going higher order mode, the refractive index suppression is more, and this can give you the lower crosstalk between the intermodal, and which can advantage for the this type of OM mode fiber. So in our case, we did record high through integration using 2 by 2 MIMO with OM multiplexing. Where, like we have been did 8 mode transmission at the same time, and we have been mode multiplexing using orbital mode can increase the fiber capacity without multi MIMO processing. And also we avoid any optical MIMO using standard hardware. So what is our hardware? You can see in our case we choose like we choose 8 mode order. We go 8 to 16 up the channel, and what we have found that we transmit the data of up to 1.3 kilometer, and that is the record for the OM mode transmission. But again, the loss is higher, and people are working nowadays how to reduce the fiber loss, especially ring core fiber, and how we are going to transmit the OM mode fiber. But for up to 1.3 kilometer, we successfully demonstrated very good result. And this is thank you from my side.
Uh, Audience, if you have any question, you can ask, or you can directly type the question in chat box. Okay, I think so. There's some question in chat box.
Yeah, yeah, we can use it.
Yes, sir. There is one question from Akansha Singh. Sir, can we use
Yes,
hybrid
yes. Model,
modulation
yes, yes,
techniques
we
in?
can use it.
Okay.
If you go to study about the like OM mode, then you can find that there are a lot of degree of freedom. It's in the classical, in the quantum is more. But now this OM mode, actually, if you can see, if you go to study OM is the most like entangled photon. So that's why OM is more popular now for the communication perspective. The problem of the study of the OM in the communication is the lack of the information about the physics. Since I did my PhD in the physics, but I am working in engineering, and currently I am working at the satellite communication and quantum communication. So what I found that the lack of the information, or lack of the understanding of the physics perspectives. Even I can tell you, if you are talk about the OM, people are studying about the RF and they stop there. But we have just saw the European Space Agency with the 9 meter 9 meter about the 9 meter like our transmission of the RF beam, we can able to show the very good result, and they are really surprised. The only the things now that as I starting up the presentation, I say the interdisciplinary research is really important, since this is there no way to we can handle the challenge. Since some of the people are very good in the optical communication, and some of the people don't know about the physics, how they are going to understand the OM, or they never understand. And I am not saying people cannot, but the problem is that if you work in a 20 year in a optical communication, you are very good in there. So, but you forget about the different challenges. Like somebody asked hybrid modulation technique. So might be he the communication physicist for sure. So that's why I say everybody is looking the problem with your own expertise, own vision, and they try to solve the problem. But OM is really an interesting topic nowadays. At least for research innovation for sure, but I am trying to push further standardization. And let's see in the coming 1 or 2 years how it will move. So with the background of computer science, is it good to have a good understanding of classical and quantum physics to excel in this? Why not? And I tell you the important is the like for me actually nowadays there no research currently like how the I tell you the European proposal is working. I am the physicist. I am working in the quantum communication. I am writing the proposal with the Korea. This guy know the quantum computer, but in my proposal some quantum machine learning need to optimize. Then another group of the Fraunhofer Germany, they are very good to making the SLM, special light modulator, but they are not aware about the quantum physics or quantum machine learning. Some of the people who like Trinity College London, they are very good in the BFM. He is very good in the computer machine learning. And then one guy from the Aalto University, Finland. I just wrote the proposal, and the combination of this, what we observed that like for the one proposal, we need all the type of expertise, but we have to share the information, and that guy also need to understand a little bit the physics. Might be you don't need the physics, a complete understanding, but when you are targeting your research, at least you have to study about that background for sure for the starting point of view. And the research is going step by step. You are not going to learn one day. Maybe you start with sometimes, and when you are progressing, the things you understand the better about your research.
Okay, sir. Uh, Thank you so much, sir. You and your team have done excellent job in this area. The session was very informative. As a co-coordinator of this event, once again, I want to thank you for your kind support and participation in Atal FDP on emerging frontiers in quantum technology and communication. Thank you so much, sir.
Thank you. Thank you very much. If you have any question, please let me know. If you want to do some meaningful collaboration, I am very happy. We have the very good quantum optics lab here. Not like this is the realistic, and we have the very good collaboration with the European Space Agency and like a main whale of the Europe, and we currently I am more focusing on industrial research, but we are still doing the fundamental research. So if someone want to do the some meaningful collaboration, I always okay to learn about that.
Sure, sir. Thank you so
Thank
much,
you.
sir.
Thank you very much.
And participants, please mark your attendance for both the session, and we will meet again tomorrow. That is the last day of this event at 2 p.m. for the upcoming sessions. Thank you. Good night. Dr. Himanshu, please stop.